Hello everyone. On the special occasion of today's session, I would like to start with a few personal remarks. I'm very pleased to be part of this special event to honor Simcha Aram. For me, he is a true role model of a scientific scholar, and I'm very grateful for our collaboration, but even more so for the personal friendship which developed from it. Today I am going to present some results from our analysis of a series of recordings of liturgical chants from Georgia, which were sung in 1966 by the Georgian master singer Artem Erkomaishvili, and which were recorded at the Tbilisi State Conservatory, the very location where I first met Simcha in 2014. These recordings have a special meaning for all of us co-authors. It was the first analysis of these data which started the collaboration between Meinhard Müller, Sebastian Rosenzweig and myself, which then led to our joint research project Computational Ethnomusicology of Traditional Georgian Vocal Music, which is funded by the German Research Foundation. This project in turn made it possible to bring Nanam Javanadze to Potsdam, where we could work together during the last 2 years. Artem Erkomaishvili was one of the last master chanters of Georgian liturgical chant and an exceptional singer and choir leader of traditional Georgian music. In 1966, 1 year before his death, at the age of 80, he was asked to perform a series of chants to save them for posterity. Since chanting was prohibited during the Soviet period, he had no fellow singers to sing with him. Therefore, he had to sing all 3 voices by himself. These performances were recorded at the Tbilisi State Conservatory using 2 tape recorders, which were subsequently operated in what is now called overdubbing. 50 years later, this setup turned out to be very helpful for the determination of the fundamental frequencies of the individual voices in our first study on this set of recordings in 2017. This is now most likely the oldest set of recordings of Georgian chants from which the time-synchronous fundamental frequency trajectories for all 3 voices have been consistently determined. Therefore, these recordings are an important resource for any attempt to understand Georgian tuning, as is expressed very nicely in the words of John Graham cited here. The starting point for what I'm going to present today was the re-release of the original audio data together with estimated fundamental frequency trajectories for all voices, beat annotations and digital scores through a web-based interface in 2020. Here I will briefly demonstrate the recording setup and the access to the web interface so that you can get an impression of this dataset. We will watch and listen to the beginning of chant number 10, Gaussian Chantana, Yesterday, O Christ. First, we will listen to the top voice recording, which is unaffected by any of the other 2 voices. Then to the middle voice, and finally to the bass voice. The middle voice was recorded against the playback of the top voice, while the bass voice was recorded against the playback of the 2 upper voices. As a side effect of the development of the score following mechanism behind the web interface, it is now possible to access the audio data on a note level, which we made heavy use of in our study. In this context, we count the time in the score on a quarter note reference time frame, which we refer to as quarter note reference system. So now here comes the sound. Now we will listen to the second segment, which contains the middle voice in the foreground and the top voice from the playback. And now finally the bass voice. The objective of the present study is to investigate the tonal organization of the Erkomaishvili dataset from several different perspectives. What we consider first in the context of our analysis are the statistical distributions of the fundamental frequency values in what we call the stable parts of the trajectories. These are assumed to be perceived as note objects with well-defined pitches, and we will refer to them as pitch distributions. All fundamental frequency samples within note events are referred to as pitch samples, and hence the term pitch in the present study should be understood as an acoustic quantity, which at best can be interpreted as a proxy to the psychoacoustic quantity which cannot be measured directly. Subsequently, we investigate the tonal organization through what we refer to as melodic step size distributions, or melodic intervals. These are the distribution of pitch differences between consecutive note events in a melody. The third perspective is via the distribution of harmonic intervals, in those parts of the pitch trajectories of different voices which belong to note events and for which concomitant pitch values are available. The general goal of our study was to develop an evidence-based model for Artem Erkomaishvili's melody generation process, which incorporates all these aspects of tonal organization, pitches, scales, melodies and harmonies in a consistent manner. I will first explain how we determined the pitch distributions and how these relate to the melodic sound scales. Our strategy in the whole study was that we did not want to exclude any data from the analysis, but apply the machine learning paradigm to let the data speak in a very strict sense. The analysis of each voice starts from its raw fundamental frequency trajectory, here shown for the top voice of chant number 8. Note that the fundamental frequencies are displayed in cents relative to a reference frequency of 55 Hz. So from the raw trajectories we determined the stable portions, which we assume to correspond to those time windows which we perceive as note objects with well-defined pitches. To illustrate that this is not a bad assumption, let's listen to the beginning of this chant again and simultaneously watch the cursor move along the fundamental frequency trajectories. The red horizontal lines, which you see here, correspond to the note objects determined from the stable portions. You will hear Artem Erkomaishvili's voice together with a synthetic signal, corresponding to the pitches of the note events. This was used to check the quality of the pitch determination. I think this illustrates why we restricted the subsequent analysis to the stable parts of the pitch trajectories. You can also see that this naturally gets rid of the sliding phases, which we definitely do not want in our analysis. One simple way to imagine the generation of the pitch distribution from the pitch trajectory is to imagine a simple bookkeeping exercise in which we move along the vertical axis and ask for each pitch value, plus minus some tolerance, how many pitch values in the complete chant fall into this pitch bin. If we do this for the whole pitch range, and if we plot the results as a histogram, we obtain the pitch histogram on the right side of this plot. What this histogram immediately shows is that the pitches are nicely structured into individual groups. The pitch values within each pitch group seem to be distributed more or less symmetrically around a center value. This suggests that we can use a very compact and elegant mathematical representation of the complete pitch distribution in a form which is called Gaussian mixture model. This is simply the sum of a number of Gaussian distributions which are weighted by different weighting factors. Each Gaussian distribution is described by a mean value mu and a standard deviation sigma. The Gaussian mixture distribution is the red solid curve which is shown here on the right side. So each of these little teeth corresponds to one Gaussian distribution which is anchored, you can think of this as an anchoring to the mean value of the corresponding pitch group. Its spread is described by the quantity sigma. For example, the pitch group with the largest amplitude of the bell-shaped curve is the one which is anchored at a pitch value of 2433 cents. The number in front of the colon is what we refer to as the pitch group index. The pitch group representing the largest number of samples in it gets the index of 0. It's this one here. We count the ones above with positive indices, 1, 2, 3, 4, etc., and the ones below with negative indices. The number after the plus-minus sign is the standard deviation sigma, which describes the spread of the corresponding pitch group around the center pitch value. You can see, for example, that the pitch group 3, this one here, has a very small standard deviation of 17 cents, and you can see that this tooth is very small. While the pitch group -5, here for example, is spread out and has correspondingly a standard deviation which is much larger, 71. But you could say, so what? Why do we actually believe that this representation is important? Well, there are two main reasons for that. First of all, the Gaussian mixture models allow us to represent the relevant information from the pitch histograms, which may consist of hundreds or even thousands of values in a few numbers, here into 10 values for mu and 10 values for sigma. This allows us to compare the pitch distribution of different chants and or the whole corpus very, very easily. Second, and this is one of the main results of our study actually, I will later demonstrate that these mu values represent the melodic scale pitches of Artem Erkomaishvili's underlying tuning system. I will show evidence that Artem Erkomaishvili seems to always have been aware of these pitch values and where the pitches he sung were in relation to them. Before I do that, however, let's look at the properties of the melodic intervals. Here you see the histogram of the actual melodic intervals between the neighboring pitch groups in the top voice of chant number 11. We can see immediately that the sizes of the melodic intervals between neighboring pitch groups ranges from roughly 100 cents to more than 200 cents, close to 250 cents. In other words, from a semitone to more than a whole tone. We have color-coded them in the three different categories: below 160 cents into blue, between 160 to 190 cents in green, and above 190 cents into red, to be able to easily identify them in the following plot. So how do they relate to the pitch distributions? In the left plot, we are looking at the top voice pitch trajectory again. This is this line here. But in such a way that we can see the melodic steps superimposed on the pitch distribution, which is shown here on the right. So the grayscale here corresponds to the probability density values indicated by the Gaussian mixture models. The horizontal magenta lines which are dashed indicate the borders of the individual pitch groups. In this figure, it is easy to analyze how the melodic step sizes develop as a function of time and how they relate to the different pitch group transitions. So the transitions from the individual pitch groups to another one. We can see, for example, that the melodic steps between the pitch group -3 and -2 take place in two different varieties, in green and blue. So in other words, in intermediate and small steps. The expected step size between these two pitch groups is shown here by the tilted number in blue, would be 163 cents. This would correspond to the differences of the pitch group centers. For the transition between the most salient pitch group, 0, and the one above, the expected step size would be 202 cents. However, in the melody, all step sizes, blue, green and red, are actually used. In other words, melodic step sizes are a very poor indicator of the distances between pitch group centers. On the other hand, the pitch distribution indicates a clear heptatonic structure with 7 intervals over an octave. The fact that the octave is stretched is not surprising. It is well known that exact octaves with a frequency ratio of 2:1 or 1200 cents are often perceived as too small, a phenomenon which has been discussed in several papers without a consensus being reached on the course. The distance between the most salient pitch group here and the pitch group 4 steps below is a pure fifth, plus minus 1 cent. An observation which also holds for many other chants. So the question which we are left with at this point is, where is actually the scale? And this question is directly linked to the question, why are the melodic step sizes so variable? To understand this better, we asked ourselves if it would matter for the step from, let's say, pitch group K to pitch group K plus 1 if the starting pitch of a note would be above, equal to, or below the center pitch value of the starting pitch group, which would be here. In other words, would Artem Erkomaishvili change his melodic step size in order to compensate for a deviation from the center pitch value of the starting pitch group? Let's define the so-called extra step size as the difference between the actual melodic step size, what he actually uses, and the expected step size for the particular transition. So the expected step size for this particular transition would be the difference of the pitch group centers, which would be 202 cents. If the deviation of the starting note from the pitch category mean value, so which is shown here on the horizontal axis, would matter, then we should see a systematic relation of the extra step size, so the deviation from the expected step size. So if, for example, Artem Erkomaishvili would start a melodic step with a pitch deviation of minus 30 cents, so 30 cents flat from the pitch group mean value, would he try to compensate for this deviation somehow by changing the melodic step size? In other words, by a positive extra step size. If he would not be aware of a pitch deviation, or if it did not matter to him, the extra step sizes should just fluctuate randomly around the horizontal axis, as sketched here for illustration. However, what really happens is something different. What we observe is a very clear and strong linear correlation between the extra step sizes and the pitch deviations from the pitch category mean values. And this is independent of which pitch group contains the starting note. The starting pitch group are color-coded in the values shown here in the legend on the right. So independent, if you're looking at the green dots or the red dots or the blue dot, we see this linear correlation. So in other words, Artem Erkomaishvili was always aware of the position of the pitch group mean values. Hence the scale was always in his head. He was also aware of any, even small deviations from these pitches. Otherwise the regression line would not have such a well-defined slope for small deviations. And third, he tended to compensate for relative deviations of the starting pitch of a melodic step by changing the melodic step size. All this demonstrates that the center values of the individual pitch groups, in other words the mean values mu k of the individual Gaussians, define the pitches of the associated melodic sound scale degrees. An important take-home message and one of the main results from our study from this is that the melodic sound scale for Artem Erkomaishvili does not require fixed melodic intervals. It rather seems to act like a set of attractors, around which the melody can more or less freely move, but to which it is always pulled back. One does not immediately see the presence of the melodic sound scale when looking only at a sequence of melodic intervals, but it always acts as constraint during the melodic development. So obviously Artem Erkomaishvili had a very good ear and very good pitch control of his voice even at his high age. On the other hand, when we look at the pitch distribution, we see considerable pitch fluctuations within the individual pitch groups. The amount of this variability is expressed in the values of the standard deviation sigma of the individual Gaussians. With a few exceptions, they show values on the order of 25 to 33 cents. One can think of a whole list of possible explanations for them, some of them intended and some of them unintended. We have tried to analyze most of these effects in our study, but due to the time constraints, I cannot go into any detail here. Let me just mention how we looked at the effect of what we call intentional pitch bending. To analyze this effect at all with the Erkomaishvili dataset is only possible because of the existence of a group of 4 chants which contain a number of identical melodic phrases. Here you see the pitch trajectories of those melodic phrases which appear in identical form in this chant group, consisting of the chants number 8 to 11. I spare you all the processing details of how we had to realign the pitch trajectories relative to a common pitch and time grid, which was only possible through the metadata in the newly curated dataset. In order to obtain an estimate of the magnitude of this effect, we analyzed the first of these phrases in a little bit more detail. This is shown here. What we observed in this detailed analysis of the individual notes was that the actual melodic intervals, which are used in the phrase, seem to be very consistently enlarged or reduced depending on the position within the phrase. And this demonstrates that the deviation of the melodic step sizes from the expected values, which is what we call intentional pitch bending, was a conscious choice of the singer. For the 10 notes in this phrase, we estimated these values in the order of 5 to 30 cents. This demonstrates that this effect is non-negligible and could therefore contribute significantly to the shape of the melodic interval distribution, as well as to the spread of the individual pitch groups in the pitch distribution. In the final part of our presentation, I'll describe now the results of the analysis of the complete Erkomaishvili dataset. The purpose of this part of our analysis was not to perform a detailed study of the properties of the individual pitch distributions of the individual chants, but to test if they share some common features in a statistical sense, which can be detected computationally. In other words, the goal was to derive scale models which jointly represent the melodic sound scales of the complete dataset in a synoptic way. For 2 reasons, this is not as simple as one might imagine. Since Artem Erkomaishvili started each chant at a different pitch, the individual pitch distributions might be shifted in pitch by an unknown amount relative to each other, even if the same melodic scale might have been employed. And here you see this for the pitch distributions of the chant group number 8 to 11. In principle, this can be corrected for by aligning the pitch distributions relative to each other using cross-correlation analysis. Since, however, the cross-correlation function is quite sensitive to amplitudes, we also need to correct the pitch distribution for the different weights of the mixture component. This process is called whitening and changes the amplitudes of the individual Gaussians in such a way that the alignment is only dependent on the interval structure of the distributions. This is what we want. Here you see the effects of whitening and alignment. The final judgment about similarity or dissimilarity of interval structure in the different chants should be made after whitening and alignment. Here we see that there is a lot of structure in common. Now we look at the pitch distributions of the top voices of all the chants. After whitening, we still don't see much because of the more than 100 distributions superimposed on top of each other. However, after alignment After whitening and alignment, we can see that a large subset of the corpus share a common interval structure, at least for the central parts of the pitch distribution. In order to quantify this common part, we calculated another Gaussian mixture model from the set of mean values of the individual distributions. This figure now can be interpreted to represent the interval structure of the melodic sound scales of all the top voice tracks in an average sense, a kind of executive summary. The interval structure of individual chants can of course deviate from this corpus level distribution in details which are averaged out by the processing. It can be noted that even at this coarse level, the interval structure of the average pitch distribution model for the top voice shows musically very interesting features. For example, we can immediately see several intervals close to pure fifth, here, 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 and here, and one close to a pure fourth. A feature which we also observed quite prominently in individual pitch distributions is the existence of rather large intervals, approximately 200 cents, between neighboring pitch groups close to the most salient one. Musicologically, this is a key finding, since it is the existence of an interval close to 200 cents which is necessary to build the 1-4-5 chord, which is so typical for traditional Georgian music. For example, we see a very clear 1-4-5 chord if we are looking at the second, the fifth and the sixth pitch group from the left. We find it extremely interesting to see that the 1-4-5 structure, which is typical for the harmonic structure of traditional Georgian music, is already visible as a melodic summary feature of the pitch distribution of all the top voices. I'll now come to the most characteristic musical feature of traditional Georgian vocal music, namely its multi-voice character. Similar to the analysis of the top voice pitch trajectories, we have also analyzed the pitch distributions for all voices jointly, as well as the harmonic interval distributions. Since there is no time for an in-depth discussion, I can only touch upon them briefly. Here you see the corpus level pitch distribution for all voices and all chants. It naturally has a larger ambitus, but the interval structure is similarly clear as for the top voice. We can also see an interval close to 200 cents right next to the most salient pitch groups. The corpus level harmonic interval distribution shows the frequencies with which the individual harmonic intervals occur in the corpus and the variability with which they were sung. We see that the most common intervals are more or less justly tuned fifth, 708 cents, followed by unison around I think it's 1 cent. Then I think the next one is a neutral thirds, sharp fourth, stretched octave, and the ninth. It can also be noted that the variability for the harmonic seventh, which peaks at 1044 cents, is much larger than for the other intervals, indicating that harmonic sevenths are realized in a variety of ways in the chants. Earlier in this talk, when touching upon the phenomenon of pitch bending, I demonstrated that Artem Erkomaishvili intentionally deviated from the melodic scale pitch skeleton quite freely, although he was always aware of its presence. Another piece of evidence demonstrating his creative freedom is the observation of harmonically driven intonation adjustments of individual voices in order to achieve purer harmonic intervals. This phenomenon has been qualitatively described in the literature at least as far back as to the early 20th century. With a newly annotated dataset, it has now become possible, possibly for the first time, to look at this phenomenon quantitatively and on an individual note level. The way we analyze this is illustrated here. The top left panel shows the pitch trajectories of two notes building a harmonic interval of a fifth. The right top panel shows the corresponding harmonic interval trajectory, which is simply the differences of the higher voice and the lower voice in the left panel. The numbers below the trajectories denote the statistical variances of the trajectory segments, in other words, the squares of their standard deviations. If the two trajectories were statistically independent, the variance of the interval should be the sum of the individual variances. If, however, the two trajectories correlate, the interval variance becomes smaller than the sum of the two variants, and the variance ratio, as defined here, should be smaller than 1. The amount of variance reduction, in our case it's more than 60%, is directly a measure for the amount of intonation adjustment. In other words, for how much Artem Erkomaishvili adjusted his lower voice to the upper voice in order to achieve a particularly pure harmonic interval. We can also see this harmonic intonation adjustment in the lower left panel, which plots the pitch sample of the upper trajectory against the lower ones. The correlation is pretty obvious by the oblique alignment of this point cloud. And here you can see which intervals are most strongly affected by this phenomenon. The histogram shows the number of occurrences of those adjusted harmonic intervals in the complete dataset, which consist of notes longer than half a second and for which the variance reduction of the interval variance was at least 50%. Not surprisingly, these are the fifth, the unison, the octave, followed by the ninth and the fourth. I'm now going to wrap up. With his performances of more than 100 chants, Artem Erkomaishvili has left a unique documentation of past performance practices. With the present study, we have tried to demonstrate that a lot can be learned from these recordings by employing computational techniques. I need to mention again that for our analysis we made heavy use of the metadata of the newly curated dataset, all of which, by the way, is publicly available. Without the beat annotation and the possibility to easily align recordings computationally to positions in the scores, our analysis would not have been performed on a note level precision. As one of our major musicological contributions, we have derived 3 synoptic scale models for the complete dataset. And despite the fact that no data were excluded from the analysis, these models, which represent the complete dataset in a comprehensive way, show remarkable, clear and stable features. The most persistent observation in essentially all chants is that their pitch group distributions contain 2 rather large intervals, approximately 200 cents, close to the most salient pitch group. Musically, this large interval seems to serve a very important purpose. It is an indispensable condition for the generation of the harmonic 1-4-5 chord, so common in traditional Georgian music. Most other melodic intervals are close to 175 cents, which might explain why the scale could be mistaken for an equidistant one. It is definitely not. Overall, melodic and harmonic scales are fairly similar, except for the first scale degree. This is understandable as well, because in an 1-4-5 harmonic chord, the second will usually be a side product of having a pure fourth and a fifth together, the difference of which makes roughly 200 cents. In contrast to an earlier preliminary study, we now see clear evidence for enlarged octaves in the comprehensive models. This phenomenon, known as octave stretching, has been discussed in several papers, for example by Burns in 1999. On the methodological side, we had to enter quite a bit of new territory. Our study introduces a new approach to generate tuning models, which are consistent with the melodic scale models derived from the observed pitch distributions, as well as with the melodic and harmonic interval distributions. To our knowledge, our work is the first study of traditional Georgian music which treats all these aspects together. In this context, Gaussian mixture models turned out to be a very efficient approach to represent pitch and interval distributions by a few numerical values. There's a lot more which they can be used for example, in the context of comparing different tuning systems, but this is left for future work. The harmonic intonation adjustment mechanism is yet another new contribution of our study. It has only qualitatively been described for Georgian music before and is the final link to understand how the music actually works. Our numerical results regarding the harmonic intonation adjustments are not really unexpected. They underline again that Artem Erkomaishvili was an exceptional singer who, when singing the middle and bass voice, was able to instantaneously adjust his intonation to achieve desired harmonic intervals at a fairly high precision, judging by the amount of variance reduction in the interval traces which he was able to achieve. As a side effect of our analysis, we learned that the analysis of melodic intervals can be very misleading if one wants to derive a scale model from audio recordings. As was demonstrated by the compensation of the deviations from the pitch group centers, the information about the scale degree defining pitches rests in the central values of the pitch groups, or in mathematical terms in the mu k values of the Gaussian mixture models. I will close by mentioning that the present talk reports only on a part of our whole study. If you're interested, you can find discussion of additional aspects, for example, on the still ongoing Georgian soundscale discourse, on microtuning, or more technical details in this monograph, which was published last year as the first volume of a new series on computational analysis of traditional Georgian vocal music. It can be freely downloaded from the Potsdam website of our project, where you will also find other resources. Thank you very much for your attention. Didi Matlova.